The next type of series that we're going to explore are called p-series, and the nth term is of the form a sub n equals 1 over n to the p. So there's some n here raised to a power of p. Now this is more like a power term in the denominator, which what we saw before for our geometric series had an exponential term. And so this is more of a power term. And it turns out that p-series are so valuable to us because we can determine convergence or divergence based solely on the value of p. And if you'll remember our improper integral work, when we had something that looked like this, we could say it was 1 over x to the p with respect to x, and we said this was the power rule for integrals. And so we have the power rule is 1 over the exponent plus 1, x to the exponent plus 1. And it turned out that for us, when p was greater than 1, if you'll look back in your notes, we knew we had convergence. So we've already talked about p-series. When p was less than or 1, we knew that the area in the plane that this was talking about diverged, or we're going to say now that our series diverges. And this is exactly what we are using to model this area in the plane. The area models the series sum. That's actually what we're using. We'll see later on that this is a test that we will use even on different types of series, not just p-series. But because this is true and because this is firmly based on the power rule for integrals, it's something that we get to count on in our series work. And it's really, really powerful because all we have to do, just like geometric series, all we have to do is identify that our nth term, that our series itself, is a p-series. So we just label it a p-series like we labeled the other ones geometric series. And then we state overtly that, hey, we know p equals this value, whatever it happens to be. And let's say we can tell that it's greater than 1. So because it's a p-series with p equals some value greater than 1, we can say it converges. Or if it was less than or equal to 1, we would say this p-series diverges. So again, this is a whole set of series that we can use for comparisons in our other tests that's really, really handy. The only difference here is that we can't know for sure what the series converges to. So we won't ever be asked to, find the value that the p-series converges to if it is a convergent p-series, where we would be asked to if it was a convergent geometric series. It turns out that there is one p-series that we see a lot, a whole lot, and it is the case where our form a sub n is 1 over n to the 1. That's what's happening here. And it is the case where p equals 1. And when p equals 1, we just said we know a p-series diverges. This particular series has its own name. It's called the harmonic series. So anytime you're dealing with this particular series, if you see the sum from n equal 1 up to infinity of 1 over n, all you have to do is state that you recognize it is the harmonic series. You don't even have to state that it's a p-series. It is a specific p-series called the harmonic series, and we all know, every mathematician who knows anything about series knows that the harmonic series diverges. So we'll see as we progress through our series work that we have to justify why we say this series converges or diverges. And we'll have to state which test, or we might even say, or the type of series so that we can determine the behavior of the series. If it's a harmonic series, it's going to diverge. If it's a p-series where p is less than 1, it's going to converge. If it's a p-series where p is greater than 1, it's going to diverge. So the harmonic series is a great series because our justification is simply to identify it. Here is the harmonic series, comma, we know it diverges. So this series also illustrates the converse of that theorem that we were talking about in our first set of videos for series. We said that if we put a sub n in this limit as n approaches infinity, and we don't get 0, that we knew that series had to diverge. We just took that on faith. It actually has a name, and we'll learn the name in the next few lessons. But this is the converse of that. Just because the limit does indeed go to 0 doesn't tell us that the series converges. If that was the case, then we would need one and only one test, and this would be it. That's not the case. It's just we're using one little twist on this that says if, and we'll look at this more when we go through the test, but if the series does converge, then the limit as n approaches infinity of that nth term will equal 0. But many divergent series also will have that nth term inside that limit as n approaches infinity go to 0. However, absolutely no convergent series that I put inside that limit will equal anything other than 0. So here is what we're using when we run that limit and hope not to get 0. Because some divergent series, the limit will equal 0, and some divergent series, the limit won't equal 0. So what we're going to do is we're going to see what's going on in that limit. If it equals 0, it's inconclusive for us, and we've got to use another test, because divergent and convergent series both inside that limit could equal 0. But if it doesn't equal 0, then we know it diverges. So the harmonic series is one of the many divergent series that if I were to put it inside that limit, I would get 0 for an answer. And I would be tempted to say, hey, that means that the last terms in the sequence are getting small enough that this thing probably converges. And as it turns out, it doesn't. The harmonic series grows, the sum grows. I mean, we're adding smaller and smaller and smaller pieces to an already accumulating sum. It grows super, super slowly, but it does continue to grow over infinity, and it diverges. So we'll revisit that later when we actually learn that test, but I want to illustrate using the harmonic series how that limit doesn't tell us about convergence. That limit really only tells us about divergence when it comes to series. Here are some examples. Not all of them are p-series, but if we find that we're in the form of 1 over n to the p, then we want to recognize what value p is. We want to tell the AP reader up front, we recognize we're looking at a p-series. We recognize p is 1/3. That is less than 1. Anytime p is less than or equal to 1, that series diverges. That's all our work would need to look like. That's pretty handy. Let's look over here. All we would have to do here is identify this as the harmonic series. And then we would have to state that we know the harmonic series diverges. That's all our work would have to look like there if they ask us whether this series converged or diverged. Here, this is a p series. We recognize p is 1/2. We recognize it's less than 1. This series diverges. The numerator doesn't always have to be 1. Remember, if I have a convergent or a divergent series multiplied by some real number value c, that real number value does not affect convergence or divergence. So I can just pull it out front and get rid of it. Here's a p series where p equals 2. That's greater than 1. When p is greater than 1, the series sum converges. Here is a p series where p equals pi over 3. So is that greater than or less than 1? Well, remember, pi is a value that is a little bit greater than 3. So this is going to be a little bit greater than 1. Well, all it's got to be is greater than 1, even just a tiny, 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 tiny bit greater than 1. And that series converges. Now, this is not a p series. You are going to be given all types of series and be asked if they converge or diverge. It becomes really important that you recognize them based on the makeup of the nth term. And we just learned that this is a geometric series. We would then have to state, we know r is -4/5. We know the absolute value r is less than 1. So we know this geometric series converges. So be on the lookout for different types of series. You're not always going to be shown just one type of series. We're going to have to recognize the makeup of that nth term, and that nth term is going to point us to either what type of series it is, or as we'll see over the next several lessons, what test we can run to determine convergence and divergence. So p series are really handy for us. We love them. We hope to see them. We get free and easy points on the multiple choice part of the exam, because sometimes they'll throw 3 series up there and say Roman numeral 1, Roman numeral 2, and Roman numeral 3, which converge or which diverge, and state the reason why, and then you have to work through all those. But p series are really handy, and they're all based on whether p is greater than 1 or whether p is less than or equal to 1. Now, our brain doesn't like greater than meaning converge. I will tell you that. You might struggle with that as time goes on. The brain doesn't like less than or equal to 1 being divergent. But you have to remember, you are in the denominator of a fraction. And so that relationship is going to be reversed because you're in the denominator of a fraction. So this is important. Those two things you're responsible for. Come to class next time and we'll work some p series homework problems.